Our first speaker for the afternoon session is Nathan Seiberg, and he'll tell us about QFT and beyond. Please.
Thank you. Can you hear me okay?
Yeah.
And you can see the pointer?
Yes.
Good. So I'd like to thank the organizers for putting together this fantastic, very exciting conference under such special, very difficult and challenging situations. I also thank them for inviting me to speak here. Naturally, I'd prefer to be in person in Rio now. The topic of this talk is quantum field theory and beyond, but what I will really be interested in is the interesting interplay between lattice quantum field theory and continuum quantum field theory. And the relation between the lattice and the continuum is very interesting, and it goes through two different perspectives. The first is that quantum field theory is enormously successful. We have no doubt that it is correct, but it's not yet mathematically rigorous. And one way to make the theory rigorous is to place it on a lattice. So we triangulate our space-time manifold. In this case, in this talk, I will limit myself to flat space-time, and we'll triangulate it with squares. So we have a square lattice. So I'm going to limit myself to flat space with periodic boundary conditions. And the main point of doing it is that when we replace our continuous space-time with the lattice, the number of variables in our theory becomes finite because we have a finite lattice. And then the functional integral becomes a finite dimensional integral, a bit large, but it's still finite. And if the target space is compact, and if the action is sufficiently regular, then our integrand is bounded, the number of integrals is finite, and the whole thing is what makes sense and is manifestly well defined. Then the challenge comes from taking the continuum limit. We introduce a lattice spacing, the distance between neighboring sites, and we take A to 0, and simultaneously we take the number of sites to infinity, holding all the lengths fixed. So we pick some, for any points that we pick, we just make the lattice finer and finer. We make this mesh finer and finer so that we get a better approximation for the continuous underlying space-time. And we also compute correlation functions at fixed position x as we take A to 0. So A goes to 0 and the x's remain finite. So this is well known, and this is one reason to be interested in the lattice as a way of making sense out of the continuum theory. I will soon say what challenges this approach poses. The other reason to be interested in the lattice theory and the interplay between the lattice and the continuum come from condensed matter physics. Here, the lattice is not just a mathematical thing that we invented in order to regularize the theory, but in reality, there is a real lattice. Here are some atoms arranged in some lattice in a crystal, and the various atoms interact with each other. And our goal is to determine the long distance behavior of the system. What does this system do when the distances are very large? And this is closely related to the continuum limit I mentioned here, because at long distances, we think of the lattice spacing as going to 0, and the total number of atoms is going to infinity. Now, starting with kindergarten, I was told that if we look at this lattice at long distances, the description of the system at long distances is by a continuum quantum field theory. Although this has not been rigorously proven, the argument goes as follows. We have a lattice, but if we look at it from afar, we don't see the lattice, we just see a smooth manifold. Furthermore, we have degrees of freedom, say on the sides or the links of the lattice, and these degrees of freedom becomes functions on space-time. And from here, going to continuum quantum field theory, the distance is very small. As I will soon argue, the situation is not that simple. In the next two slides, I'll present some challenges for these two views. First, what's challenging here? Here we start from a given continuum field theory, and we would like to place it on a lattice. And then we would like to take the continuum limit, namely remove the lattice and view it in the continuum. So the first question to answer is, does the limit exist, and is it independent of the details of the lattice? This is a bit reminiscent of the situation in defining an ordinary integral. When we define an ordinary integral and we divide the integration region into strips, we have to prove that the resulting continuum integral is independent of how we sliced the integration region. And it's also independent of whether we cover it with rectangles or with trapezoids, etc. Similarly, here, we have to argue that the limit exists. And if you and I regularize the theory slightly differently, we are still going to get the same continuum answers in the limit. This still needs to be done. Another challenge that I will talk to at length in this talk is that some continuum theories depend on the topology of field space, which in turn relies on the continuity of the fields. So on the lattice, the degrees of freedom are not continuous. The degree of freedom at one lattice site and at another lattice site have nothing to do with each other. There is no notion of continuity. But as we take the continuum limit and we replace the lattice by a continuum, we think that in the continuum, the configurations become smooth. And now a new thing happens because in the continuum theory, we have a map, a continuous map from some space-time manifold to some target space. And the collection of these maps can break into classes which are topologically different. This distinction between the classes is associated with new terms we can add to the action, for example, theta parameter. It's associated with certain global symmetries, for example, winding number, and also connected to anomalies. I'll talk a lot more about this thing below. Here, I would simply say that until recently, I thought that there is no way to get these phenomena on the lattice, because on the lattice, nothing is continuous. So anything that depends on the continuum configuration being smooth cannot exist on the lattice. There are also other challenges in placing a continuum theory on the lattice that I'm not going to address here, but they're very, very interesting and important questions. One is that some quantum field theories do not admit a suitable Euclidean lattice action. There's a lot of work on this, how to put self-dual forms or fermions and how to write them on the Euclidean lattice. But as far as I can see, there is not completely satisfactory solution to the problem. The second problem is even more serious, that there are some continuum quantum field theories, for example, the famous 2-0 theory in 6 space-time dimensions, and for which there is no continuum Lagrangian, let alone a lattice version. So here we need to define the quantum field theory. We could not even write a continuum Lagrangian, let alone regularize it by a lattice. I'm not going to say anything about these last 2 points. Let me move to the second aspect of the lattice versus continuum. And this is when we start at short distances with a lattice model, and we are looking for its low energy, long distance effective description. And the low energy effective description, we expect it to be a quantum field theory, a continuum quantum field theory. This was the case, for me at least, until recently. But during the last several years, there were some new lattice models that people wrote down, different kinds, such that if we try to take their continuum limit, we do not end up with a standard continuum quantum field theory. Personally, I should say that when I first heard about these things, I was completely convinced that these examples will go away, because there is no way that quantum field theory would fail to describe these phenomena, but I was wrong about that. These models are not going away. And these exonic models are of different kinds. One of them that I will discuss in detail later in the talk was first presented by Parmakanti, Balance, and Fisher in 2002. I'll call it the XY Plaquette model, and I'll describe it in a lot of detail below. Its continuum quantum field theory is not a standard continuum quantum. Its continuum limit is not a standard continuum quantum field theory. The second, in a totally independent line of research, is called Fractal Models. And these are the pioneering authors, and there's a lot of follow-up on that. And again, these are very interesting theories, and they do not have a continuum limit, do not have a standard continuum limit. What's special about these models? So there are many different models, and every one of them has different peculiarities, and they fall into various classes, type 1, type 2, etc. But there's one thing which is common to all of them. All of these models are characterized by an exact or emergent subsystem global symmetry. I do not know the reference. As far as I know, this was the first paper, Laura and Fratkin, but for all I know, there could be earlier papers on the subject, and there's certainly lots of follow-up papers. What's a subsystem global symmetry? An ordinary global symmetry is a symmetry that, say, multiplies the degrees of freedom. So we have a complex field phi, and we multiply phi by a phase, the same phase everywhere in space. So at a given moment in time, we act with a symmetry transformation, and we multiply the degree of freedom phi by the same phase independent of x, y, and z. Here, we have separate group elements for different subspaces. So for example, we can multiply a complex field by a function independent of y and z, but an arbitrary function of x. What this means is that the symmetry group is enormous. It's infinitely larger than for an ordinary symmetry. This subsystem symmetry is the thing, as far as I can see, is the thing that really drives the show here. And it is the origin of all the peculiarities of these models. I'm not going to discuss it in detail here. It will be easier to describe later when I present concrete examples. But I'll say here only a few facts about it. The fact that we have this subsystem symmetry, that the symmetry group is enormous, and we have different group elements at different positions, say, as a function of x, it means that observables at the lattice scale A can vary at the lattice scale, and hence in the continuum limit, they will be discontinuous. Let's consider an example of some correlation function, and such that all the charges are balanced, say exponentials, and all the charges are balanced, and such that the subsystem symmetry is preserved. If we take one of the operators and move it a little bit in x, now the charges are no longer balanced because we have separate symmetry element at different values of x. So the correlation function was not zero before, and it's zero now. So even without looking at the details of the system, it's clear that correlation functions are going to be discontinuous in the continuum limit. And if we take various derivatives, they will be singular in the continuum limit. So that by itself tells us that there's something very interesting and very unusual here. Second, the symmetry group is very large. And the large symmetry group typically has very large representations. So if the ground state is in a non-trivial representation of this huge symmetry group, it is going to have a very large degeneracy, typically of a size exponential in the size of the lattice. This means that if I take the continuum limit and the number of sites in the lattice goes to infinity, the ground state degeneracy will be infinite. So if we naively try to take the continuum limit, we are guaranteed to have correlation functions that are discontinuous or even singular, and an infinite number of ground states. More physically, this reflects UVIR mixing. Phenomena at short distances, like on the scale of the lattice spacing, affect answers to questions at long distances. How many ground states the system has is clearly a long distance question, and the answer to that depends on what the lattice spacing is. And if we make the lattice spacing smaller, holding the physical length fixed, the number of ground states is going to grow. Similarly, the discontinuities in the correlation functions. I'm not going to elaborate on it here, but I want to point out that this is reminiscent of some string constructions, specifically little string theory in quantum field theory or non-commutative spaces, which also exhibit similar UVIR mixing, and they are equally puzzling and interesting. So what should we do about this? One approach is to say, okay, these systems cannot fit into continuum quantum field theory, and we should just move to another problem. I think this is too fast. So together with my fantastic postdoc, Shu-Heng Shao, is now moving to Stony Brook, we decided to fit these models into the framework of continuum quantum field theory. And it's clear that we're going to have to bend the rules because these models do not fit in the standard framework of continuum quantum field theory. And once we start bending the rules in field theory, which barely makes sense, in fact, we cannot even make it rigorous, it's clear that we're going to face problems. We are walking on very, very thin ice here, and we might not get to the other side. So we decided to do it anyway, guided by the existing lattice models. And we asked ourselves, what can we do to fit the existing lattice models and their known long distance behavior to fit it in the language of quantum field theory? So what did we do? This was the new element. First of all, the space-time symmetries, we're not going to have Lorentz invariance or rotation symmetry. This by itself is not a big deal. It's easy to take a continuum quantum field theory and explicitly break the rotation symmetry. This does not lead to any interesting subtleties. Second, we are going to impose these exotic global symmetries, specifically the subsystem symmetries that I mentioned earlier. That by itself opens the door to all the subtleties I discussed, because it will necessarily lead to the kind of singularities and discontinuous fields that I mentioned earlier. We also considered gauging these subsystem symmetries. And if we gauge the subsystem symmetry, the transformation parameter of the gauge theory must also be discontinuous. And as you notice, we are getting further and further out on our thin ice that we walk on. This thing necessarily means that we have to study discontinuous fields and gauge parameters. Now, on the lattice, everything is discontinuous because, as I said, the value of configurations at one point and another point have nothing to do with each other. There is no sense of continuity on the lattice. Our rules about the allowed fields was such that the allowed configurations are more smooth than on the lattice, but not as smooth as in the continuum. We made up the rules so that we land on our feet, so that we reproduce the lattice answers. This, of course, raises interesting questions of universality. Specifically, if we expand the effective action in powers of derivatives and we have discontinuous fields, high derivative terms could be as important as the low energy terms, and we are going to lose universality. So all these things are things that we have to keep in mind. As we saw, this actually does not happen for most observables. But one should be very nervous about that. And when I gave talks about that, people always told me this has to be made more rigorous, because this is even less rigorous than standard continuum quantum field theory, much less rigorous. So we ask ourselves, does this make sense? Can we really make sense out of such theories? And in order to address this question and to explore it, I'm not going to have a digression now and discuss another system which we understand very well, a system that does not have all these subtleties. I'm going to review things which are known for decades. And again, it will be the canonical example of a lattice model and its corresponding continuum theory. I'm going to review known things, and at the end, I'll say a few new things. And then I'll use this technology to address these subtle systems, the exotic systems. And the model I'll discuss is the XY model in 1+1 Lorentzian dimensions, or in 2 Euclidean dimensions. There's huge literature on this subject, really tens of thousands of papers. There's a lot of earlier work. I'll focus mostly on this paper from '77. And of course, there's a lot of follow-up. So what's the model? We are back to the lattice. Every time I go back to the lattice, I'll put this picture here. The lattice is Euclidean time. Time is Euclidean. So we have 2-dimensional Euclidean lattice. We can put it with periodic boundary conditions. And on the sides of the lattice, we're going to put phases. So we have a circle valued field phi at every point on the lattice. And we're going to write an action, the coefficient beta, with some of all the links, the nearest neighbor links of the lattice. Delta mu is the lattice derivative. It's the phi at this point minus the phi at this point. And then we take the cosine so that it would be compatible with the periodicity of phi. So this is the model. Finite lattice, finite number of variables. Phi is integrated between 0 and 2 pi on every side. The action is finite, so the functional integral is completely well defined. In fact, we can compute it in the computer. We can put it on the computer and can get whatever we want as a function of beta. The main characteristic feature of this model, and it's also the origin of the name XY, is kind of rotations in the XY plane. The reason, the characteristics property of it is that it has a global U1 symmetry, and using the string terminology, we'll refer to it as momentum. We can take this phi, which is defined on the lattice, and shift it by alpha. So we take phi on every side in this Euclidean lattice and shift it by the same constant alpha. And clearly the action doesn't change because the action depends only on the lattice derivative of phi. The next thing we could do is make beta large. If beta is large, we penalize in the action configurations where phi varies largely from point to point. So the dominant configurations are configurations where phi is nearly the same at nearby points. And then we write the continuum action as follows. I should add parenthetically that it's known that in the functional integral, the dominant configurations are discontinuous, but I want to emphasize that this has nothing to do with what I'm talking about here. So what about this model? So this is the lattice model. This is the continuum model. This model is well known, and it comes under the name of the C=1 compact boson. And unlike the lattice model, which is nonlinear because it depends on the cosine, this model is quadratic. The action is quadratic in phi. The equation of motion is a PDE, which is linear in phi. This model is exactly solvable. We can compute the correlation functions on any genus very explicitly. There are closed form formulas for the correlation functions. It clearly makes sense. This continuum limit differs from the lattice model in several crucial details. It has two global U1 symmetries, and for every U1 symmetry, we have its corresponding netter current, and this is the netter conservation equation. The momentum symmetry was already on the lattice. This is the symmetry that shifts phi by a constant everywhere, and this is the corresponding current, and it is conserved because of the equation of motion of phi. The second symmetry is a winding symmetry, and again, I'm using the high energy physics or the string terminology. In condensed matter physics, it's called vorticity. This is an emergent symmetry. It did not exist on the lattice. It does exist in the continuum, and it measures how many times phi, which is circle valued, winds around space when space has a circle. So if space or space-time has a circle, we can measure how many times phi measured around the space. And this winding number is a conserved charge in the continuum, but not on the lattice because phi is continuous. Furthermore, I'm not going to elaborate on it here. These two symmetries have an 't Hooft anomaly between them, a mix between the momentum and winding. And this 't Hooft anomaly is at the root of many of the interesting features of this model. Another important fact about this model is that it enjoys self-duality, known in string theory as T-duality. And this is a transformation that exchanges beta with 1/beta, with some 2 pi squared that depends on your normalization. It also swaps the momentum and winding symmetry. It's important that the winding symmetry is not present on the lattice. And since the self-duality swaps momentum and winding, it cannot be an exact symmetry of the lattice. In fact, it maps large beta and small beta, but the corresponding between the previous lattice model on the previous slide and this continuum model is correct only when beta is large enough. So now we ask ourselves, how much of this continuum story on this slide, which is different than what we had in the lattice on the previous slide, how much of that can be presented on the lattice? So our goal is to find another lattice action such that all these properties, which are very intrinsic to the continuum, are present already on the lattice. And on the face of it, it looks almost impossible because how can we have winding symmetry on the lattice? After all, on the lattice, phi has different values at different sites. How can we have anomalies on the lattice, and how can we have this T-duality? So we are going to follow a lot of existing literature. I actually don't know the original paper, the original places this appeared, but some ideas that I'm going to use definitely appear in an early paper by Gross and Klebanov, and then paper by Sachdev and Park, and perhaps many others. And what we're going to do is what in condensed matter is called suppress the vortices on the lattice. But I'll do it very explicitly here. So we are going to use a Villain formulation of the model. This was invented by Villain, of course. We replaced the circle valued phi field that existed on every site with the real variable phi at every site. And the fact that phi is compact will be implemented by declaring that this system has a Z gauge symmetry. The way we do that is by introducing gauge fields, integer valued gauge fields, n mu, on the links of the lattice. So on every link here, we have an integer variable, n mu. And then instead of having the cosine interaction, we have this square interaction. This lattice model with this quadratic action is quite similar to the original action we started with the cosine interaction. And it has a gauge symmetry. We can shift phi by 2 pi times an integer, arbitrary integer at different points in space-time. And the action remains, gauge invariant remains invariant if we simultaneously shift the gauge field by a gauge transformation. This is the lattice derivative of n. And you can check that this is a symmetry of the action. Once we have this extra variable, phi is now real and n mu is integer. Once we have this integer field, there are more terms that we can write on the lattice. There are more gauge invariant terms than we can write. And specifically, we can write the curvature square of this z gauge field. This is the analog of f mu nu square for continuous fields, but now it's for this z gauge field. And we can multiply it by a coefficient kappa. For kappa equals 0, we have the original model, this one. But for non-zero kappa, we can turn on this term and continuously deform the model to another model. We're going to be particularly interested in the limit kappa going to infinity. Because as kappa goes to infinity, the field strength or the curvature or the value of this term on every plaquette of the lattice is constrained to vanish. This means that the z gauge field, with gauge fields and mu, the z gauge field is flat. There's a very effective way and very efficient way to implement this constraint. And we refer to this action as the modified Villain action. This is what we had before. And instead of keeping this term with kappa and sending kappa to infinity, we're going to replace this term by a Lagrange multiplier, phi tilde, which sets the constraint that the field strength vanishes. So on every plaquette, we add another variable, phi tilde, so that when we integrate over phi tilde, it forces this combination to vanish. And it does the same thing as sending kappa here to infinity. Since this is an integer, this n is an integer, its variation, its derivative is also an integer. Phi tilde is periodic. So this is the lattice model that we can study. And it turns out that this lattice model is very similar to the continuum field theory or the C equals 1 compact boson, except that it's on the lattice. Again, I emphasize, this is a nice finite action. The functional integral is manifestly convergent. There's nothing divergent about it. All the correlation functions make sense. So what are the properties of this lattice model? First of all, it's free, just like the continuum model, because it's quadratic in the fields. Second, it has global symmetries. It has the same momentum symmetry that we started with, shifting phi by a constant. We can see that phi is shifted by a constant here. That's a symmetry because delta mu kills it. And phi doesn't appear here, so that's clearly a symmetry. And there's a corresponding netter current. This exists on the lattice with the cosine interaction, and it existed in the continuum theory, and it also exists here. But what's interesting in this model is that we have another symmetry, which is the same as the winding symmetry of the continuum theory. We can take this Lagrange multiplier phi tilde and shift it by an arbitrary constant independent of x, y, and x and tau. I should say that this was done with my two fantastic students, Pranay and Hota, and with my fantastic postdoc, Shuhen Shao. Hota is moving to MIT and Shao to Stony Brook. This is the conserved netter current, and notice that it's very similar to the continuum current. In the continuum, we had epsilon mu nu, d nu phi, and here we have this current. Also, these two currents have a mixed and 't Hooft anomaly already on the lattice. I'm not going to do it here in detail, but I want to point out what the main point is. The symmetry acts locally on the fields. So we shift phi by a constant or phi tilde by a constant. But unlike the momentum symmetry, the winding symmetry is not a symmetry of the Lagrangian density. This term is not invariant under this shift. Instead, it transforms by a total derivative, total lattice derivative, which sums to 0 over the lattice. And therefore, e to the action or e to the minus the action are invariant, but the Lagrangian density is not. This is the underlying reason why a 't Hooft anomaly is possible in this system. So in this sense, we have here an 't Hooft anomaly in a finite system. It's a 't Hooft anomaly has nothing to do with divergences, in a system with a finite number of degrees of freedom or on a lattice. So this is almost as simple as it gets. Also, we have integer values, integer parameters here on the lattice, integer fields. So we can use Poisson resummation. This is an exact manipulation of the partition function or the functional integral. And as we do that, n mu is gone by the Poisson resummation, and we have a new integer field, n mu tilde. And what happens is that the fields phi and phi tilde switch their roles. Here, phi looks like a dynamical field, and phi tilde is a Lagrange multiplier. After the transformation, phi tilde is the dynamical field, and phi becomes a Lagrange multiplier. And if we perform the transformation, it exchanges beta in 1 over beta. So all these properties that we saw in the continuum and did not exist in the original lattice action with the cosine, they exist in this action. So after this aside, we can finally move to the exotic model. And it will be, I'll be very quick because it will, the discussion here will mirror the discussion I've just had of the ordinary XY model. So the exotic model is the model of Parmacanti, Balance, and Fisher. We call it the XY Plaquette model. Unlike the previous example, now we are in 2+1 dimensions. So this is the first difference. We again use a Euclidean lattice and a Lagrangian formulation, and we put phases e to the I phi on every side. The first term in the action is exactly as in the previous case. We have cosine delta tau phi. This is time in the time direction. We just have phi here minus phi here, delta tau. This is delta tau phi. And to make it consistent with the periodicity of phi, we write it as a cosine. Here we have a difference. Rather than having interaction or couplings along links, we have couplings around plaquettes. So space is two dimensions. So we have delta x, delta y phi. This is the double space derivative around the plaquette. So it's phi at this point, minus phi at this point, plus phi at this point, minus phi at this point. And then we take the cosine of it. Again, this is a well-defined action, so we can start playing with it. And it has the following symmetry. First, we can shift phi by an arbitrary constant independent of x, y, and tau. That's clearly a symmetry of the problem. But we can do better than that. We can shift phi by an arbitrary function of x plus an arbitrary function of y. This term is clearly invariant. And here, the double derivative kills these terms. This is an enormous symmetry group. Because if we look at space, we can rotate all phi's in this row by a phase and rotate all the phi's in this row by a different phase and all the phi's in this row by yet another phase. So this is an enormous symmetry group. And now we're going to do what we did before. When beta non and beta are large, we can approximate this action by a continuum action. And this is the continuum action. And this continuum action is quadratic. So it seems like we should be able to analyze it using standard quantum field theory techniques. Open your favorite quantum field theory book. The first thing you learn is how to deal with free scalar field theories. So here is a free scalar field theory. We can try and analyze it. So together with Xu Heng Xiao, we analyze this model in a lot of detail. And these are the features. First of all, the model is free. It's quadratic in phi. Second, because of the derivative structure that we see here, some discontinuous field configurations are not suppressed. Consider a configuration where phi is an arbitrary discontinuous function of x independent of y. Then this term in the action vanishes. Normally in the field theory, we have a two-derivative term, dx phi square or dy phi square. And therefore, if we have a discontinuity in phi, the action of such configurations is infinite, and they're suppressed in the functional integral, and therefore we don't have to discuss them. Here, discontinuous configurations do exist. As a result, some observables are discontinuous and even singular. And we computed some correlation functions exhibiting this behavior. This is the sign of the UVIR mixing. Second, the symmetries. Very much like in the ordinary C=1 model, we have two global symmetries, and they satisfy a peculiar net current conservation equation. And it's peculiar because we have dx dy of the same object jxy. As a result, the charge is the integral of j tau over some spatial manifold. Here we can integrate it over x at fixed value of y, and it is conserved. Similarly, we can integrate it over y at fixed value of x, and it is conserved. Hence, this is a subsystem symmetry. The first such symmetry is the momentum symmetry. This is the current. and it's conserved because of the equation of motion. This is very much like in the C=1 boson. The momentum conservation, this is target space momentum. This symmetry is there because of the equations of motion or in the action. But we also have a new symmetry that did not exist on the lattice. We can call it the winding symmetry. Again, it's a subsystem symmetry, and this is the current. And the current satisfies this differential equation because here we have d tau dx dy phi, and here we have dx dy from here, I think d tau. So this is a conserved current. Also, we have a mixed anomaly between these two symmetries. So this is very reminiscent of the C=1 boson, except this peculiarity. We have momentum symmetry and winding symmetry and a 't anomaly between them, and it really calls for T-duality. And in fact, if you follow the standard rules of T-duality, you can see that we have exact self-duality, which exchanges μ0 and mu, which is dimensionful in this case. It also swaps the momentum symmetry and the winding symmetry. So this is very interesting, but it raises many, many questions. One question is specific to this model, but actually much broader because the same question arises in all our models. How should we treat more precisely such continuum field theories with discontinuous fields? This is very tricky. Maybe we're doing something wrong. Maybe we have dependence on other higher derivative terms. What exactly are the rules with these discontinuous functions? How do we add them? How do we multiply them? How do we differentiate them and so forth? Notice that these are questions which are not rigorous even by physicist standards, because what we're willing to tolerate for the ordinary C=1 boson might not be good enough here. The second question reflects the similar question I asked earlier about the C=1 system, is how much of that depends on the continuum limit? What did we do? We started from a well-defined lattice model, and we took its continuum limit, and then we analyzed its continuum limit, and we found some results that are true on the lattice, but also many other results, like an emergent symmetry, a 't anomaly, self-duality, etc. How much of that is true on the lattice? And what we should do, in hindsight, looks completely straightforward. Let's try and imitate what we did to the ordinary XY model. And this is what we did in the recent paper with Pranay, Hotta, and Shuhei. We're going to repeat the same discussion we had before, but now for the XY, we did it for the 1+1 dimensional XY model. Now we're going to do it for the 2+1 dimensional XY Plaquette model. So this is the lattice action we started with cosines. The cosines are complicated, so we want to write it in Villain form. It's straightforward. We'll replace this cosine by delta tau phi square, and we'll replace this cosine by delta x delta y phi square. So that will just copy it from here, and this copied from here. But phi has to be single valued. Sorry, phi has to be circle valued. And if phi has to be circle valued, delta tau phi square is not good enough. So we add a Villain field, an integer field on the time-like links, very much like what we did in the ordinary XY model. So that's what we do with this term. Here, we need to add a funny gauge field with two indices. Notice that not only are these two indices in this gauge field, they are symmetric indices rather than anti-symmetric. But anyway, it's an integer gauge field, and we replace this action by this action. And for large beta naught and large beta, these two actions are clearly the same. So here, just to summarize, phi is real, n tau and nxy live on the temporal links and the spatial plaquettes. They are integers. And we have a Z tensor gauge symmetry. Phi is identified with phi plus 2 pi m, where m can depend on x, y, and tau. N tau undergoes an ordinary gauge transformation, and nxy undergoes a funny gauge transformation. Now we follow the same steps we did before in the XY model, in the ordinary XY model. This is the field strength or the curvature of this funny gauge field. We're going to add it with the coefficient kappa. This is the field strength square. We add this gauge invariant, and we add it with the coefficient kappa, and we take kappa to infinity. So the equation looks a little bit complicated, but it's not that difficult. If kappa is infinite, we replace this term by a Lagrange multiplier. So what do we have? This is the time derivative term as we had before. This is the double space derivative term that we had before. They replaced the two cosines that we had before. Phi tilde lives at the center of the cubes, and it is circle valued, and it acts as a Lagrange multiplier, multiplying this gauge invariant field strength of the tensor gauge field. So this is our action, and again, it is completely well defined, and it turns out to be very similar to the continuum version of the XY Plaquette model that we discussed earlier. First of all, it's free because it's quadratic in the field. Second, it has exact global subsystem symmetries. For this subsystem symmetry, we already discussed it before. We can shift phi by a function of x plus a function of y. This term is invariant because the time derivative kills it. This term is invariant because of the double derivative. And this term is easiest to check because it's independent of phi, and therefore if we shift phi, it doesn't change. We also get a new symmetry, a winding symmetry. We can shift phi tilde by an arbitrary function of x plus an arbitrary function of y. So these terms are independent of phi tilde. They are obviously invariant. This term is non-invariant. The Lagrange density is non-invariant, but it transformed by a total derivative such that the sum of the total derivative, lattice derivative, is 0. Therefore, the system has subsystem momentum symmetry as it originally has, but it also has a new subsystem winding symmetry that earlier did not exist on the lattice, but existed in the continuum. Now it exists already on the lattice. And as in the C=1 model, we have some integer gauge fields here. The action is quadratic, so it really asks to use Poisson resummation. And if we do Poisson resummation, these integer gauge fields are gone. Instead, we get new integer gauge fields we can call n tilde. The fields phi and phi tilde switch their roles. Phi, which was dynamical, becomes a Lagrange multiplier, and phi tilde, which was a Lagrange multiplier, becomes a dynamical field. It also exchanges this term with this term and inverts the coefficients. So this is very similar to what we did in the ordinary XY model. So what did we do? We started with an ordinary system that we fully understand, and we found a new presentation of its lattice model that exhibits more of the features that exist also in the continuum. And we also have some new model, exotic model, that we also did it to, and we landed on our feet and we reproduced all the answers we got in the continuum, even though the treatment on the continuum was not rigorous. Now it's completely rigorous because it's done on the lattice. So motivated by that, we've explored lots and lots of different models. So we analyzed many known models in quantum mechanics, where we put the Euclidean time lattice. So time goes in steps, it's Euclidean time. We also explored many models in 1+1 dimensions, 2+1 dimensions, 3+1 dimensions, various models with global U1 symmetry or ZN symmetries, and also gauge U1 of different forms, and ZN gauge symmetries of different forms in all these dimensions. All these are ordinary models, well understood. They have a known lattice model. They have a known continuum description. There are many properties of the continuum description, and now we can see all the properties of the continuum model on the lattice. So all these models exhibit on the lattice the emergent symmetries of the continuum theories and their 't Hooft anomalies. Also, the dualities are the same as in the continuum. So for example, 3+1 dimensional or 4-dimensional Maxwell theory has an electric one-form symmetry on the lattice, but no magnetic one-form symmetry on the lattice. The magnetic one-form symmetry exists in the continuum, but not on the lattice. In the new version of the lattice model, both the electric and the magnetic symmetries are present on the lattice, and the 't Hooft anomaly between them. Also, the continuum theory has self-duality. Now the self-duality exists already on the lattice. So this was with ordinary systems to make sure we know what we are doing and we land on our feet. No shocking result here, except that perhaps that it can be done. But then we applied it to a lot of exotic models that had existed on the lattice before. Then with Shu-Heng Shah, we explore them in the continuum. When we explore them in the continuum, we had to face this question of discontinuous fields, exactly what are we doing? But now we can go back to the lattice and do the same thing, namely use Villain formulation, modify the Villain formulation to suppress to set the gauge field, the Villain gauge field, to make it flat, and then explore the model, explore its symmetries, explore its duality. So there's a long laundry list of models. There are various gapless models with U1 subsystem symmetry. I'm not going to go through the list. Various gauge theories and non-gauge theories. All of them can be put on the lattice with this prescription that we used, and we landed on our feet. There are also gap models with ZN subsystem symmetry. Many examples, including one of the most famous Fractal models, the X-cube model of Vj high and full. Now, in all these cases, the emergent symmetries and the dualities of the continuum theory are manifest already on the lattice. So that's very good, because one could have been uneasy about the way we treated these models. Now we derive the same thing on the lattice in a deformation of the original lattice model, which is expected to flow in an appropriate limit to the same continuum theory. So we can view these lattice models as a rigorous justification of the treatment of discontinuous field in the continuum field theory description of these models. I'm very happy to report that all our previous results, some of them appeared questionable, were confirmed by this lattice treatment. So let me summarize. This was a long script. We said that it's common to use lattice to define a continuum quantum field theory, but it's not always possible. Sometimes it is, sometimes it's not. So there are some big challenges here. Going in the opposite direction, the low energy limit of a lattice theory is expected to be a continuum quantum field theory. But as I mentioned, that's not always the case. There are these newly found exotic lattice models, which are challenging counterexamples because they cannot be written at long distances as a standard continuum quantum field theory. And if you go back and ask, why does it happen? In all the examples that I know of, it happens because of some kind of UVIR mixing. And the UVIR mixing makes the ordinary field theory description puzzling. The UVIR mixing originates from a subsystem global symmetry, different symmetry element at different values of X, say, or more complicated ones. This in turn leads to large ground state degeneracy, which is infinite or not even, and perhaps even not well defined in the continuum limit. And we have discontinuous and even singular observables in the continuum limit. So this is why it is challenging. So all these things seem to be incompatible with the standard framework of quantum field theory. So as I said, facing this problem, one could say maybe quantum field theory is not the right language to describe these models, and therefore maybe we should just work on a different problem. Maybe working on this problem is misguided. But if we try to fit this phenomena into the framework of continuum quantum field theory, we really have no choice but to consider such field theories with discontinuous fields. The treatment of the discontinuous fields is subtle, and I'm not sure we did everything correctly. And therefore, it's good to have a good way to regularize it. So what we did was to consider many examples, both standard models and some of these exotic lattice models. And we applied the following procedure to all of them. We deformed them slightly by writing them in Villain form. That was the first thing, with some integer valued fields on the lattice. And this made them free and easier to analyze already on the lattice. The most significant deformation constrains the integer value gauge field to be flat. We did it with the Lagrange multiplier. Once we have done that, the resulting lattice model, this modified Villain form of the original model, exhibits all the global symmetries of the original model, but also new ones and the 't Hooft anomalies and exact dualities. These are precisely the new global symmetries and the 't Hooft anomalies and exact dualities that we had found earlier in the continuum treatment. Therefore, these models are very close to the continuum models. So this was a long summary. Let me summarize with the summary of the summary. Continuum quantum field theory description of exotic models with subsystem global symmetries necessarily involve discontinuous fields. There's nothing we can do about that, and we'll have to face this question. Second, we gave a modified Villain version of these models, and they provide a rigorous justification of the analysis of this continuum quantum field theory. So I'm out of time, so thank you and stay healthy.
Thanks. Are there any questions? Greg Moore has a question.
Hi, Adi.
Hi, Greg.
Yeah. How explicit can you be about the renormalization group flow? I mean, by any means, perhaps by block spin in these kinds of exotic lattice models.
They are completely free, so I can solve the lattice model exactly.
But as
these lattice models, these modified Villain models, are exactly free. They are solved the same way you solve the continuum.
No, I got that. But supposing I want to write some kind of renormalization group flow by block spins. I mean, for example, supposing I'm trying to understand the strange behavior about the ground state degeneracy.
Yes.
How could I mean, usually the renormalization group is used to try and justify standard continuum expectations about continuum field theory from lattice models as lattice spacing goes to 0, right? So Wilson and all that.
Yeah.
I'm saying what goes wrong with the renormalization group?
Right. So people in the condensed matter literature try to do that in various models. And the way they do that is basically have a kind of peculiar version of the renormalization group already on the lattice. We just want to compare the system with size L to the system with size, say, L+1. And they do that by tensoring another topological field theory to add the extra degrees of freedom. It's not as clean and as straightforward as in the ordinary renormalization. But very deeply, you see that it has to be like that. Because the main thing to remember about these models is this UV-IR mixing. IR phenomena are very sensitive, or at least some of them are very sensitive to short distance physics. We do not have the standard decoupling between UV and IR. We do not have the standard separation of scales between the UV and IR. And therefore, standard renormalization group picture, which assumes separation of scales, is going to be tricky.
So technically, what goes wrong if I just try and do some naive block spin type?
Well, you're not going to work.
I know you just explained to me it's not going to work, but technically, what goes wrong?
Well, you're going to miss more degrees. So what do? You try to integrate out modes, and you realize by assuming that you don't change the long distance behavior, right? That's what you do. You try to hold the long distance behavior fixed and integrate out mode and adding some more degrees of freedom. That's not going to work. So if you forget the long distance physics, you just integrate out modes at short distances, you introduce long range correlations in the answer. And the reason for that is the subsystem symmetry. If you integrate out modes that would transform under the subsystem symmetry, it induces long range correlations. So depending how you want to set it up, it's not going to work. Either you introduce non-locality as you do that, or if you hold the long distance fixed, you cannot write a local action that does the job. Did I answer your question?
Sort of. Thank you.
Okay, I see there's another question in the chat. If we consider lattice versions of topological quantum field theory, the quick answer is yes. In fact, you can think of Dr. theory as a version of this story where you start from Zn gauge theory, and then they impose that on the lattice, the curvature of the Zn gauge field is 0. So all the holonomies around the triangulation, as long as they do not wrap, so every closed loops, which is topologically trivial on the lattice, is 0 in the Zn gauge theory. You can do that for all, not for all Chern-Simons theories, but for all the abelian ones. And you can even do that for some of these fractal models, which can also be described as a Zn gauge theory on the lattice by imposing an extra constraint on the curvature.
Thanks. There's one more question from Marco Gualtieri.
Hi, thanks for your talk. I was just wondering, if you could say a few words about the 3+1 Maxwell theory. What does it look like, and what did you find when you studied
Okay, it's
it?
very simple. You write basically the gauge. You instead of the gauge group on the so you start from lattice gauge theory, where you have links which are phases, and now we put on the phases not we put on the links not a phase but a real number. And then instead of f mu square, we write the naive f mu, which is linear combinations of a mu's around the plaquette. And then we need to restore the fact that the gauge group is U1 rather than R. So we add a discrete value B field for every plaquette. So the cast of characters is real gauge fields on the links and integer gauge fields on the plaquettes. These are like B fields. And we write the action F minus B quantity squared. That's the model. And then we need this is just the Villain version. And what we also do is we would like to make the field strength of B 0. So we add the Lagrange multiplier. So the field strength of B, we can call it H, which is linear combinations of B's associated with cubes. We add the Lagrange multiplier A mu tilde, and we add it times this H. The resulting theory has both the electric and the magnetic symmetry. The electric symmetry shifts A, the magnetic symmetry shifts A tilde. And if we perform the transformation of them, you can check that there's a mixed anomaly between them. Also, the exact self-duality of Maxwell theory is present already on the lattice. There are these integer gauge fields. You can perform Poisson-Ray summation on them, and you find the original action with beta becoming 1 over beta.
Thanks. There's one more question from Gleb Aminov.
Yeah, a naive question. Do I understand correctly that the statement is there's no way to take a continuous limit and get non-singular fields or non-discontinuous fields?
No, if you take the continuum limit in an ordinary system, so first of all, on the lattice, you can start with the original system, or you can use the modified Villain. These are different lattice models, and on the lattice, they are different. Now we can try and take the continuum limit. Then first of all, we claim that in a suitable range of parameters, the continuum limit of the original model and the modified Villain model are the same, and they are the same as the naive continuum limit. When we try to analyze the properties of this continuum limit, depending on the model, we do or do not need to face the question of discontinuous field configurations. If we do that for ordinary models, like the C=1 model, we don't have to face this subtlety. For the other models, we do. So we had some rules in calculus how to deal with that. But if one is confused, we can always go to the modified Villain version. And the modified Villain version is as easy to work with, almost as easy as the continuum theory, except that we don't have to address this question of discontinuous field configuration, because everything is completely well defined. We know what we're doing on the lattice.
Yeah, but the question is like, if you steal your it's like taking the limit of large number of particles. We should still believe that if you look far away, or like if you look at a system that has a very small spacing and a lot of sides, you should still have some kind of understandable limit, continuum limit. That's the question.
Yeah, I sympathize with this thing, and this is to a large extent correct, but there are some observables which will be infinite in that limit. And this is true in the exact answer, where we have a lattice model, we solve it, and that's a property of the answer. So this should not be used as criticism of the continuum theory.
Yeah,
that's regularize it and find a finite answer.
Yeah, that's a question of how to take a proper limit. Probably that's.
Well,
Thank you.
The point is that it's not how to take the limit. That's what I emphasize. There's only one way to take the limit, and this is the answer. We can take the lattice model, for example. Let's discuss this XY plaquette model. We have a well-defined lattice model with two dimensionless parameters, beta and beta 0, either with a cosine or with its modified Villain version. And we can just take the continuum limit by making the size of the lattice infinite and compute correlation functions in distances that go to infinity or held fixed as we take A to 0. There's no ambiguity how to take the low energy limit. So there are correlation functions that can be computed on the lattice, can be computed on the lattice in the limit, and we get an answer. And the answer is well defined whether we want it or not. If it's discontinuous or if it is singular, so be it. There's nothing we can do about that. But there's no ambiguity there.
Thank you.
Thanks. So the next talk will start maybe 6 minutes after the hour. And in the little break, there's just one more question from Mykola Didoshenko.
Hi. I have some vague questions. So since you're venturing into this exotic territory and willing to accept UV-IR mixing, would it make sense to search for some connections to non-commutative field theories?
Okay, so naturally the thought crossed my mind, but I don't see it here. There are some similarities between what we do here and the field theories of non-commutative space. Let me mention the similarities. First, the structure of the derivatives, the fact that we have the x dy phi rather than, so there we also have the x phi square, but here we have the x dy, but not the x square phi. So that's one similarity. Second similarity is in the physics of this. In the non-commutative theory, as we make the momentum larger in the x direction, the object grows physically in the y direction. The theory in the non-commutative space can be thought of as a theory of dipoles, so that as the momentum in one direction grows, the system grows in the perpendicular direction. And what we see here is kind of similar to that. I didn't get time to describe it. We are writing a paper about lots of correlation functions in these systems, and they exhibit this peculiarity that large momentum in x, or if we show distance in x, is correlated with large distances in y. And that's very similar to the non-commutative geometry. Having said that, I don't see any further relation between these two UV-IR mixing. Personally, I believe that all these are just the tip of the iceberg. There are many systems which have UV-IR mixing, which for various reasons we have not explored. And whenever we found one of these systems, it was totally by accident that we stumbled on them. So as far as I know, in gravity, it's very common that we have UV-IR mixing, but even in theories without gravity, the little string theory exhibits UV-IR mixing, and we stumbled on it. The non-commutative field theory on a non-commutative space has a UV-IR mixing, and again, we stumbled on it. And the same thing is true in these systems. People did not find these systems by saying, oh, can we find a system that exhibits UV-IR mixing? That's not how these systems were discovered. They're discovered by looking for other things, and people explore them, and now we point out that they have this phenomenon. Since these systems were found in accident, I believe there are many other systems like that that exhibit such peculiarities, but we haven't found them yet.
Okay, thank you.
Thanks for the great talk. I think these are all the questions.
Thank you.